Hello and welcome back to EGR 151 Electrical Machinery. In this unit, we're going to be taking a look at various measuring devices. These include devices used to measure current, voltage, resistance, and we'll also look at both DC and AC units, and for that matter, analog and digital. The whole idea is to familiarize yourself with these pieces of equipment so when you first run into them in a laboratory environment, you'll have some idea how to operate them. So what are we trying to accomplish in this unit? Well, once you're done, you should be able to connect a voltmeter to a circuit, also an ammeter to a circuit, and be able to connect a wattmeter and ohm meter to circuit as well. In addition, you should be able to read an analog unit and a digital unit for that matter, a little easier on a digital unit, and we need to be able to use an oscilloscope. Oscilloscopes are designed to look at primarily alternating current, but other wave shapes as well, and we need to interpret what that display means. In addition, of course, we need to know the units associated with it. So, for example, a voltmeter measures voltage, an ammeter measures amps, an ohm meter measures resistance, and a wattmeter actually measures power, right? So the units are directly connected to the names of the various meters. So here are the basic types: voltmeter, ammeter, ohm meter. As I said, they're designed to measure the associated electrical quantity, and we'll look at both analog and digital units. You probably won't run into analog units too often anymore. Pretty much everything is digital, but they tend to be a little easier to understand how the meter actually functions, to look at the analog side, and then, of course, the digital side is tends to be more done with electronics, and as a result, it's not so straightforward what's going on inside. So let's start the discussion with a voltmeter. We'll start, as I said, with the analog device. As you can see, this is set up here where we have a needle, right? That needle is actually going to measure the voltage. We have a series of different ports that we can connect together and a series of switches. We'll talk a little bit about those. One key thing about a voltmeter is it needs to be connected to the circuit when it has power on, right? The fact is, without power, you're not going to generate any potential difference. So for example, if you wanted to measure the voltage of a battery, you'd need to connect it directly across it. So actually current will flow through a voltmeter. Now, one key thing about all of our devices is you need to be kind of careful to prevent them being overloaded. In fact, we'll talk about how they're set up, oftentimes with various types of resistors internally, to prevent large power surges. These tend to be pretty delicate devices, and if they were to be able to receive a large power surge, you would burn them out or potentially damage them. So how do we avoid that problem? Well, in a voltmeter, we know the current is going to be running through it. So what we do is built in internally is a large resistor with a known resistance. Turns out actually the devices that we generally use, these coil devices here, actually all measure current. So what we're doing is we're limiting the current flow with a known resistor based on that, and then we have a calibrated needle system here, calibrated gauge. So when we measure the actual current, it's converted directly over to voltage. Now, we want to make sure that the resistor matches the correct range of voltage, right? You couldn't use one resistor necessarily for all the volts, or when you get to very low voltages, you'd get very inaccurate readings. So it turns out that what we have set up in pretty much all of our meters is a switch of some type, and it allows us to switch between different volt ranges, right? And it does that by increasing or decreasing the resistance. If we have a high resistance, we can have a high voltage range, and the current will be limited. On the other hand, if we have a lower range, we want it to still remain accurate, we need to use a smaller resistor. Now, keep in mind you want to use the smallest value you can, right? For example, if you only had, let's say right here we see 50 volts. If you only had, say, 45 volts, you wouldn't want to use any of these higher ranges, right? Because it would look smaller and smaller on the dial. So generally what you do is you start with a very large range and you slowly move the dial down till you get a reading that is shown accurately on the dial. Now, how this is accomplished is internally, we have a set of resistances in series. As you switch between those, you're going to be able to get different ranges, right? So ranges is the maximum values when the dial is pinned to the other side. It would be potentially 30 volts, 60 volts, 300, etc. And we do that by putting in larger and larger resistances to limit the motion of the voltmeter. Similarly, an analog meter essentially accomplishes the same thing, but again, we want to make sure that the ammeter does not potentially get burned out. So we want to make sure that we always have some type of load associated with it. Again, it has to be with the power on. So we couldn't just, if you just connected a battery and ran it through an ammeter, you'd get a sudden surge in current and damage the ammeter. So we need to make sure the load is connected, right? That'll give you an accurate understanding of the current flow. Now, internally in the meter, so that all of the current doesn't go through, we have what's referred to as a shunt. Right? Essentially, a shunt is a very large, physically large resistor that has a very low resistance. Right? Bigger resistors tend to have lower resistance because there's larger paths for the current to flow through. And this shunt is what's going to set the calibration here on the ammeter. Right, so whatever, you have to know what the shunt is. This is, again, internal to the meter, and it's all set up ahead of time. Of course, we want to be able to read a wide range of currents. So we have the same idea of a switch. This is when we have a ammeter that is a multi-range one. Of course, we're still talking about analog meters. By the way, all these meters are DC, direct current meters. Right? We'll talk a little about AC in a bit. And this is done by having different shunts, right? So higher resistances will be for smaller amps. Lower resistances will be for larger amp ranges, right? Because we want more and more of the current to go through it. Now, a key thing about this is when we're switching between those, the shunt always has to stay in contact. Right? If the shunt ever is removed from contact, suddenly the ammeter is going to get a power surge. So we use what's referred to as a make before break switch. And essentially what it does is before it breaks contact with this resistor, it makes contact with this one. Obviously, for an accurate reading, though, you have to have it fully engaged into this switch. So make sure whenever you're operating them, it is important that you take care that the shunt is never disconnected from the meter. If it was to get disconnected, you would very likely damage the meter. So let's take a brief amount of time and talk a little bit analog AC meters. This is for alternating current. Keep in mind, we can't just use a simple needle, right? The fact is the needle is actually measuring current. It uses an internal magnet to move that around because alternating current is essentially going positive, negative, positive, negative. Anytime you connect alternating current to a DC meter, you will very likely get a zero reading, right? Essentially just cancels it out. So how do you sort of fix that? Okay, well, the technique is to use a transformer. Right? We haven't really discussed transformers yet, and until we do, you don't really need to understand exactly how a transformer works, but the idea is it allows us to convert AC over into a waveform we can actually measure, and you can see, again, multiple shunts. In this case, it can be used to increase the range, right? Allow you to create higher levels of current, but because of the setup of the transformer, it actually can't be allowed to go lower. Right, so there's no way to decrease their range. Now, another common device used to measure current is a clamp-on device. This is known as a clamp-on analog ammeter, and instead of actually being connected to the circuit itself, it actually just has a loop that you connect over. Right? You can see it right down here, clips right on. What happens is internally, once that clip's closed, that closes the circuit, and what it does is it generates a flow of current, right? And when it does generate that flow of current, by the way, it's done through the magnetic field. Remember, we talked about all current creates a magnetic field, right? When it generates that magnetic field, that is sensed by a device inside. This is a semiconductor known as a Hall generator. This is a very simple Hall generator, known as a basic Hall generator, and it actually measures the Hall effect. It was discovered in the late 1800s, and it allows us to measure voltage without having direct flow. Right? So in this case here, what happens is the current is flowing through here, right? This is the current we're measuring, and its magnetic field is going to be distorted, right? That distortion is going to create a voltage, right? In this case here, we use a permanent magnet to bias this in one direction or the other. One of the nice things about these setups is they actually will work with AC because we can have it go in either direction. We can bias it in either way, and it will measure the voltage. Notice it'll go positive, negative, depending on how we have this magnet set up. Lastly, let's talk about ohm meters. Ohm meters clearly are designed to measure resistance. Of course, the units of resistance are ohms. You'll actually rarely find a ohm meter as just a standalone unit. They exist, but more commonly they're integrated with other functions, including a voltmeter and oftentimes an ammeter, all built into the same unit. And these official names are known as a volt, ohm, millimeter, also referred to as multimeter. And they actually contain the ohm meter within it. Turns out there are two kinds of analog ohm meters. These are series and shunt units. Series units are designed for measuring larger resistance, while shunt units are designed to measure smaller ones. In fact, you may actually have to have multiple ohm meters because they only work within a certain range of resistance. Now, one key thing about this that's a little different from the ammeter and the voltmeter, obviously the voltmeter and the ammeter have to be connected to power. This, of course, is what we're measuring. We're measuring power, right? So we have to have an applied voltage to measure voltage. We have to have a power supply to measure current. But resistance is actually a passive quantity. Resistors have the same resistance value whether power is running through them or not. So ohm meters are not actually designed to handle circuit power, and so you never want to connect an ohm meter up when the circuit is actually powered on. Potentially you could damage the ohm meter, but regardless, you're not going to get an accurate reading because they're not set up to work that way. Now, lastly, let's talk a little about digital meters. We're not going to get into a lot of details about the internal functions of a digital meter. That's beyond the scope of this course. Obviously, there's some very complicated electronics taking place inside these meters. So we're just going to accept in terms of their overall function. That's all you really need to know. Start with digital ohm meters. They, of course, are going to display whatever the resistance they're measuring, right? They're going to be done in a digital display, so a numerical display, so there's no movement taking place. And essentially, just like most of the devices, they're going to be measuring another quantity, in this case, the voltage drop. So they put a small amount of power through them, and they measure the voltage drop. Similar to analog ohm meters, you never want to connect these to the circuit when power's on, because potentially they can get damaged. Obviously, they can get current surges. They're not set up to handle full circuit power. Lastly, let's talk about digital multimeters. They are by far the most common type of meter you're going to see used in industry and in laboratories. They're designed to measure continuity, right? So do we have a closed circuit? They're designed to measure voltage, current, and resistance. Obviously, there's limits. They can't do a huge range, but a pretty good range. And they'll actually give you the value of any of these in a numeric display. So an actual number will appear on the screen. And of course, it will also tell you what units you're dealing with. So again, they usually have a switch at the bottom designed to switch between multiple settings depending on what you want to read. Let's take a look at that. Now, just like our analog ohm meter, digital ohm meter essentially measures voltage drop, right? So we need to have a power source. Potentially could be a 9-volt battery. That's a very common power source. Going to come out, come through a current generator, and we have a set amount of current that's going to go through a resistor, right? And based on that, we actually are measuring the voltage, but the device often then converts it directly to resistance. So you need a power supply, and it has to be processed, right? And an exact current is going to come out, and based on that. And just like other ohm meter, other devices, you'll have switches to switch to different ranges. Start with a high range, then drop it down. Now, the last of the devices we're going to look at in this unit is the oscilloscope. Right? It's a little more complicated device for certain. Take a look over here. It has a screen with a readout. It could be an analog readout or it could be a digital readout. Most of the ones you're going to see are digital. A large number of switches over here to control various settings. We'll talk a little bit about those. And then, of course, a number of ports for connecting up your various probes, right? Where essentially conductors that allow you to attach out to different parts of the circuit. Now, all an oscilloscope really is a voltmeter, right? It essentially measures voltage. So what you're seeing on the screen is various voltages. Now, why they're not just a value is it's a voltage over time. So what this is showing is how the voltage changes over time. In this case, would be connected in multiple locations, right? This can be done with an old CRT where a trace would actually measure out. That's what the analog devices do. Digital, on the other hand, actually processes it and converts it over to a signal to a digital screen. So if you take a look, here's that two-dimensional screen that's going to be on the front of it. It's going to measure two things. As I said, it's going to be voltage, right? Voltage is going to go up and down here on the y-axis. Right? Above this point is positive, below this point is negative, although you can adjust that value. Going to have a series of divisions here, right? Each of these divisions is divided into 10 subdivisions. And then along this direction is going to be time, right? So the x-axis is time, the y-axis is voltage. So for example, here you're seeing a square wave that goes negative, has a negative voltage for a series of amount of time, and then goes positive, has a positive voltage for an amount of time. Don't worry too much about it if you're not really following this. We'll get into a lot more detail when we talk about AC current. Another quantity that you can get from an oscilloscope is the frequency, right? Frequency essentially tells you how many cycles are going to go by in a given time. Higher frequency, more cycles. So this is measured in a unit known as hertz. Hertz is essentially the number of cycles per second. So for example, if you have a 60 hertz cycle, there are 60 of these waves every second. On a scope, you can measure the distance from the beginning of the cycle to the end of the cycle, essentially the period of this sine wave, and using quick mathematics, you just find the reciprocal of that, and that'll tell you the number of cycles per second or the frequency. A common device used with oscilloscopes are attenuation probes or attenuated probes, and essentially what these allow us to do is work with larger voltages. Right? Keep in mind, oscilloscopes are relatively fragile devices to a certain extent, and when we deal with large voltages, we want to make sure they don't actually make it into the scope and damage it. So an attenuation probe will allow us to step that voltage down. So for example, the most common attenuation probe is a 10-to-1 probe, and essentially what it does is it takes that voltage and reduces it by a factor of 10. As a result, if you were to measure on here, say 5 volts, the actual voltage that the attenuation probe would be connected would be 50 volts. Right, so it's a way of protecting the oscilloscope and stepping down, or if you want to think of it the other way, it's a way of measuring higher voltages than the scope could normally handle. Now, here are your various controls. What we want to basically do more than anything else is set how much volts each of these various divisions are. Right? This is one division, 2 divisions. These individual ones are subdivisions. There's 10 of them. This is 1 division, 2 divisions, 2.5 divisions. So by changing this dial, right, you can change the volts per division. Now we're showing 1 cycle, but the fact is we can have multiple probes in here. So we can have channel 1, channel 2, channel 3, channel 4, and they're going to be displayed, particularly in the digital unit, they're going to be displayed in different colors. Right? So that's where you saw that yellow waveform, blue waveform, pink, green, etc. Right? Other things you can change is things like AC, ground, DC, etc. A whole pile of different things can be done. What's going to be displayed as channel 1, channel 2, both, etc. These are analog controls. You're actually physically changing the setting inside. These are digital controls. And you'll notice on the digital controls, you can raise or lower those a set amount. So you can have sort of infinite controls. These are discrete. You can only switch between setup values. What we use an oscilloscope for is to look at the waveform. Things like how often does it repeat? Does it go positive then negative, or remain positive and stay positive? For example, this would be referred to as a DC waveform, although it's changing. Right, it's always above 0, right? So it's always positive. So that would be thinking of DC. Specifically, this would be, I think, a DC clipped waveform. But you can measure things like friction, frequency, the voltage, etc. Obviously, knowing the resistance, you can change that to current, and our all of our other rules that we've used along the way, like Ohm's law, etc., still apply when dealing with an oscilloscope or any of these other meters. Now, the last of the setups we're going to use is what's known as a bridge circuit. This specific one here shown on the right is a Wheatstone bridge. Right? And generally what these are designed to do is to exaggerate the change in a small value. So it's designed to measure small changes in things. So in this case here, what we have is we have 2 resistors, resistor 1, resistor 2 of known resistor. We have an unknown resistance here. We have an adjustable resistance here. And the idea is to determine what the voltage flow is, right? And what this allows us to do is determine very small changes in resistance, right? It also can be used with inductors and capacitors and allows us to amplify the effect. Right? The fact is, what we are actually measuring voltage. That's what we'd be measuring here in this galvanometer. But the idea of this is to measure small changes in resistance. Right? A small change in this resistance over here will be exaggerated by this setup. Fact is, if all of these resistors were the same, there would be no resistance or no voltage between those. So this changes that dramatically. Obviously, we have internally in our various devices, we're going to have different resistors to bias this depending on what we want to measure. So in summary, voltmeters are designed to be connected directly into the power, right? We're actually measuring the voltage, so we have to put it across an applied voltage. As a result, they have to have very high resistance because a high resistance is going to limit the current flow, right? In terms of how you go about reading it, one, you got to start out with some idea of what you want to measure. And then, of course, you have to adjust the meter. And then you adjust the meter so that the full range value is above that, right? So one of the common techniques is going to the highest range and then gradually dropping it down. That's if you don't know what the quantity, what the overall quantity is going to be close to, but you can drop it down to eventually you find the right range for that one. And you want to use essentially the smallest range possible because that's going to give you the most accurate reading of the meter. In terms of ammeters on the other hand have a very low resistance, right? They have to be connected in power, right? They're essentially measuring when the power's on, so they need to be connected in series, and we'll notice that they have those built-in shunts, so the current actually goes essentially bypasses them, right? That's your standard ammeter. On the other hand, if it's a clamp-on meter, right, one that loops on, has a closed loop, it actually measures the current flow by changes in the magnetic field, right? That's that Hall effect. That you do have to, of course, close the loop because you need to have a conductor that goes around to measure the strength of that magnetic field. The last of the devices of the standalone devices is our ohm meter. Of course, this is designed to measure resistance. It does have to have an internal power supply, right? Because the fact is we don't have the power on. When you're using an ohm meter, the power is off in the circuit, so we have to generate a small amount of power. This can be usually done with the batteries, oftentimes a 9-volt battery, and judging by the amount of the known voltage, you can determine how much current should flow through it and use that information to determine the resistance. Again, just a straight Ohm's law calculation. And that's done all internally in the meter. The meter's calibrated, so the output reading is going to be in ohms, but that's what's happening internally. Most common device that you're going to see is digital multimeters. Right? They're designed to actually display whatever value, whether it's current, voltage, or resistance in a digital display. So it's actually going to be a set of numbers. There's no actual, dial or needle or anything. And keep in mind, they're going to have a limited number of limited range, but generally it's a very high impedance, so it can handle most of the material or most of the readings we need to do. The last of the devices we covered in here is our oscilloscope. Right? Keep in mind, oscilloscope is essentially a fancy voltmeter, but it's a fancy voltmeter that shows the voltage over time, and as a result, you can actually see the waveform. And in terms of the waveform, one of the common things you want to determine is the frequency, and essentially you determine the period, right? The period is the time of one cycle, and then you find the reciprocal of that. Right, and that's the frequency. So whatever the time is for one cycle, 1 over that is the frequency. Now, in addition, we of course have digital meters. Particularly digital ohm meters, they put power through, measure the voltage drop, and from that you can determine the resistance. The last of the measuring tools we discussed was a bridge circuit. And of course, bridge circuits are designed to amplify small changes in things like resistance, inductance, and capacitance. And by the way the resistors are configured, for example, in a Wheatstone bridge, we can determine the changes of a small variation in resistance and get a very accurate value for these. So the bridge circuits allow us to do that. As always, I recommend you make sure you read your text. I always suggest you do that before you go through this presentation, but if you haven't already, definitely get to it. In addition, there are multiple resources on the course space for you to take a look at, and as always, if you do have questions, you can definitely get in touch with me.